Hey there, class. In this video, I'm going to walk you through running a one-way repeated measures Anova in SPSS. I'm going to go through the same example with the caffeine and memory example that we worked through by hand in the notes and show you how we would actually do that in SPSS. On Canvas, you'll find this document that I have pulled up right here. It includes steps for running a one-way repeated analysis. A one-way repeated measures ANOVA in SPSS. So it has a step-by-step guide right here. It shows you, it gives you a screenshot of how the data should be entered into SPSS. It gives you the syntax if you would rather use the SPSS syntax window. I'll show you that as well too. And then I kind of just go through the output and annotate it. I'm going to run through it with you and talk with you about it too. But just so you know, you have everything here. It'll even say in here, we can ignore this table. We can ignore this when there's the column means. There's our post hoc comparisons. So it should be pretty self-explanatory. So the first thing we need to do is enter our data into SPSS. And notice how the data are entered. Each dosage of caffeine, each repeated measure that we had is on a column. And there were 5 individuals, if you remember, in this example. And so we put each individual on a row. So person 1, we have when they received 100 milligrams of caffeine, this was their memory score of 30. When they received 200 milligrams of caffeine the next day, their score was a 28. There we go with 300 milligrams and then 400 milligrams. So you can see, and then we do the same thing all the way down to person 5 and enter their scores. So that's how the data are entered into SPSS. To run the analysis, I'm going to show you how to run it with syntax and then with the pull down menus. To open a syntax file, you just go to File, New, Syntax. And then you can type in the command. I just happen to know it's GLM, so it'd be MG100, MG200, MG300. You don't have to, MG400 be our repeated measures. I don't expect you to know these, know the commands by heart. So, what you could do is just copy and paste my syntax into the syntax window to run it. And also gave you an SPSS syntax file on Canvas, so you could use that as well. And this is just saying there's within subject factors, we named it dose. It has 4 levels. We want estimated marginal means or post hocs. We want a table for the dosage, and we want to adjust the p-values using Bonferroni, and then print some descriptive statistics. So anyway, that's if you wanted to use the syntax editor. The other way we'll use it is through the pull down menus in SPSS. And if you do this, it's also good, well, I'll talk about that when we get to it. It's also good to print it instead of just running the analysis. So then if you need to use it later, you can just redo it. But anyways, I'll get to that in a second. I'm getting a little ahead of myself. So to run the analysis, we go to Analyze, General Linear Model, and Repeated Measures. So Analyze, General Linear Model, Repeated Measures. And then we get this little dialog box. We need to name our repeated measures variable. It defaults to just factor 1, but we can name it whatever we want. I named it, I think, in the output as dose. So what dose of caffeine are you getting? And it has 4 levels, right? It was 100 milligrams, 200, 300, 400. and then we'll click add. We're going to add that, and then we're done defining our repeated measures. So now we need to say, okay, which variables in the data set represent these different repeated measures, or within subjects factors is what SPSS calls it. So we would just go and drag these over to our different and then if you get them out of order, you can use this to sort of rearrange where they are. The next thing we'll click on is options. We can get some descriptive statistics, estimates of effect size. If you want observed power, you can get that as well. You can see lots of other tests, and we'll use some of these other options when we talk about mixed ANOVAs as well. If we want post hoc test, for the repeated measure variable, they're actually in the EM means box, and we want estimated marginal means, or different post hocs for our different within levels of the doses. We would then say we want to compare the main effects, and then want to know what kind of adjustment we want. Least LSD, or least significant difference, is no adjustment to the p-value. It'd just be like separate independent t-tests between each group. We can do a Bonferroni adjustment or a SADAC. We're going to go with a Bonferroni adjustment here. See the post hoc here, where it's actually saying post hoc, notice that it's blank in here. It's post hocs for between subject factors, and we don't have any between subject factors in this case. And then we would just, now this is what I was talking about earlier. What I would suggest then is using this paste function. And what it did, notice it didn't run anything. What it did was it opened a syntax window, and it just pasted our commands in the syntax window, which instead of you writing it out yourself like I did in this syntax window, it'll paste it in there for you. So this is helpful for if you're doing, say, this project for your dissertation, and you have to come back and do the analysis again. Say you entered some data in incorrectly, you don't have to go through each of the pull-down menus and remember what all you selected again. You could say update your data and then just run this syntax again. And that just makes your life a little bit easier down the road. So notice here's your SPSS output. You see it prints that little syntax right up there at the top. You get, the names of your repeated measure variables, some descriptive statistics. Again, I believe these are will be the column means in our notes handout. We can skip the multivariate test table for right now. We'll talk about that a little more when we talk about Anova. Here is our test of sphericity here. And here what we're looking for is really wanting to fail to reject the null hypothesis. So we're looking for a significance level above our alpha level. It's sort of like the test of homogeneity of variance with the t-test or between subjects ANOVA. The null hypothesis here is that we meet the assumption of sphericity. It's basically that the variances and covariances among all of our variables, or our repeated measured variables, are equal. And so this is saying that, yes, we do meet the assumption of sphericity. So we could either, here is our, that it calculates a statistic called epsilon here. And this epsilon kind of quantifies the degree of violation from sphericity. And so if the closer epsilon is to 1, so an epsilon of 1 would mean that the data perfectly exhibit this assumption of sporosity. You know, the variances and covariances are basically exactly equal between the among the repeated measures. So this kind of quantifies the degree of that relationship. So it's still not perfect, but this is saying that it's not too far, off. There's the Stevens multivariate text in there. He actually recommends that he didn't even look at this sporosity test. He says just completely ignore it. And his recommendation is to always report the greenhouse geyser statistic. And his reasoning sort of is that if we meet the assumption of sporosity, that the greenhouse geyser, the adjustment that it makes to the degrees of freedom is sort of minimal, and that if we don't meet it, that it's a more appropriate test anyway. So like say this was statistically significant, what we would do is we would ignore the sporosity assumed line and report the greenhouse geyser anyways. His suggestion is just to ignore it completely and always use the greenhouse geyser. And he also says that, you know, the test of sporosity is also highly dependent on whether the data are normally distributed or not. And the test is kind of wonky when the data aren't normally distributed. So that's the other reason why he just kind of ignores the test. His recommendation is just ignore the test altogether and report the greenhouse geyser statistic. You see here, it doesn't really make a difference. In our case, they're both statistically significant. You can see the adjustment that it makes to the degrees of freedom. When we calculated this by hand, you know, here are the sums of squares that we calculated by hand, the degrees of freedom and the mean square values we computed by hand. You can see how the greenhouse geyser and these other two also adjust the make an adjustment basically to the F test, to the significance value of the F test, to take into account the violation of the sporosity assumption. So here really, you know, whichever one we go with, it really didn't matter. They were all statistically significant, indicating that that memory scores change or differ depending on the amount of caffeine consumed. We'll ignore this table now. This table would be important, say, if we were interested in looking at like a trend analysis, and we were interested, say, like time was our repeated measure variable, and we wanted to look at, you know, the change over time. And so we would test whether the change has a linear trend, a quadratic trend, a cubic trend. So in our case, it's going to test like a linear, see if that's linear, quadratic, and cubic, because there are 4 repeated measures, and you can always test up to 1 minus the number of repeated measures. So we would ignore this. We ignore this for now. We'll ignore the test of between subject effects because we don't have any between subject factors in our case. And here are our post hoc tests. You know, we saw that, you know, the memory was different. Memory scores were different depending on the level of caffeine consumption. And so these are then our post hoc tests, or what SPSS calls estimated marginal means. And here's our pairwise comparison table. It's very similar to the post hoc table you would get out of between subjects Anova. You can see that the 100 and 200 milligram dose did not significantly differ. The 100 and 300 milligram dose did not significantly differ, but memory scores between the 100 milligram and 400 milligram did significantly differ. You can, basically all the differences were with the 400 milligram group, significantly differed between the 100 milligram and 300 milligram group. And if we go to, if we look at the output that I have on Canvas, you can see here also computed Cohen's D's for the differences between these groups, and to compute the standardized mean difference, or what we're calling Cohen's D here. Basically all you do is you take the mean difference from the table and then divide it by, so we need a variance estimate to divide it by, we're going to divide it by the square root of the mean square error term from our within subjects effects table. So we're going to divide it by this 9.4. And so, you know, which one, you know, if you use sporosity assume or greenhouse gas, I just use the sporosity assume since that's the one we calculated by hand. It's a judgment call either way. I think most like online calculators, if you were to find one of those, use this mean squared value, but you could also use the greenhouse gas one if you want to be consistent. But that's how you would get an estimate of effect size for the post hoc comparison difference there. One thing I just realized I forgot to mention in the tested between subjects, within subjects, it also gives you an estimate of effect size. Remember when we conducted a one-way between subjects ANOVA, we would calculate either eta squared or omega squared to assess the proportion of variance in the dependent variable that was explained by changes in our independent variable. That's what we can request here and get out of here too. That's when we ask for estimate of effect size. So what this is saying is that 86% of the variability in memory scores can be explained by changes in the amount of caffeine that we're giving individuals. So changes in memory scores within individual, we can explain 86% of that variation is how you would interpret that. And you can see it should be in our, there it is. So in our output here, you can find it. And so that's pretty much all for the one-way between, the one-way repeated measures ANOVA. A lot of this output we're going to see again when we cover mixed ANOVAs as well, where we have both within subjects or repeated measures and between subject variables, and then some of the other output tables that we ignored this time will make more sense. On the handout, I've also linked to 2 other SPSS walkthrough videos. I think in the second one here, he's doing a trend analysis. If you're interested in that, you can see here. And then another one in here, they also have where they violated the assumption of sporosity. And he actually goes through, you know, he shows you like maybe why that's happened. You know, he'll run a correlation between the variables. He'll look at the covariances among the variables so you can see how different they are, and that's probably why we're violating that assumption. So if you're interested in a lot of that, these are some good videos you can go. I think this one ends up going up to like 5 parts. Once you get to the end, it'll say click this button to go to the next one. You can handle it. Anyways, if you have any questions, concerns, you know, don't hesitate to reach out to me. And best of luck. See you in the next video. Thanks.